All right, welcome back. We're now going to actually take a look at how we implement this sum function, which is something really worth looking into. And I kept most of the illustration from last time to really show you what the stack looks like when we make this call, and that will help us understand the implementation. So the first thing is that the way we implement a variadic function is by relying on an abstract data type known as a parameter pack. This is a concept, this is an abstract data type, an abstraction that basically captures the arguments that we're passing into our function. It's a package containing all the arguments that we care about. So it's a data structures, and it's an abstract data type, a data structures, and it has operations to actually manipulate it and navigate inside this thing, which we call a pack. Okay? So the representation of the abstract data type is known as a C-type, known as a VA list, variable argument list, right? A VA list is a parameter pack. And parameter pack, by the way, is the terminology that we will use in the C++ implementation. So I'm going to use the same one for the descriptions of C, right? So my variable argument list is a parameter pack. It's an abstraction that represents this, and it has a number of operations to manipulate this and be able to navigate the insides, the guts of that parameter pack. Fundamentally, you need to think of a parameter pack as a vector, but that vector contains objects of potentially different types, because each object having a different type can have a different size. That's the case in printf. After my format string, I can find a string, a double, an integer, a long, a pointer. So these have different types, but I can package them inside an array, inside a vector, and I care about their type so that I know how much space each one of them utilizes, and I know how to navigate this parameter pack by computing addresses. So the basic operation we have is to go to the beginning of a parameter pack with a variable argument start method, right? So this method or function allows me to navigate and get this first ping pointer here, which is the start address of my parameter pack. So this is something I get with a VA start, right? It gets me to the beginning of the parameter pack. Then in my parameter pack, I can advance and use that ping pointer and move it to the next element inside the parameter pack. And that is done with VA arg, right? VA arg, variable argument list arg, allows me to take that ping pointer and get the address of the next one, which is, of course, this block where the value 20, I hope it's readable, yes it is, where the value 20 is located. And of course, by repeatedly calling VA arg, you can keep moving to go to this address, then this address, then this address. So you can keep moving it. And clearly, VA arg will take into account where we are, and then it will take into account the type of the thing at that location so that it can compute the address of the next one when you make the motion. Now, of course, you can, once you're done and you have read all your argument, there is a third one to say, I am done navigating my argument pack, and you need to declare that you don't want to manipulate it anymore with VA end. That's it. Those are the three methods for manipulating a parameter pack. So we're going to handle this thing starting from the first address where it is. So let's take a look. First, before we take a look, a couple of rules that are worth remembering about conversions. The first thing is that if you see a null PTR C++ style, it will always be converted to a void star. Because remember, when we're looking at variadic function, we're looking at a C feature, essentially. So a null PTR of C++ is just a pointer to an unknown type. It's a void star. That's how the conversion happens. If you're passing a float, it will always be converted to a double. So if I make a call, imagine that we have some float, which is another variadic function that works over float, and I say, oh, there is an integer that tells me how many floats, and then I have 3 dots behind. If I actually use it, and let me illustrate a call to that, if I call some float saying 3, I can pass something like 2.5 3.14 and 2.71, if I do that, these things, even though I'm passing floating point, they will be upgraded automatically to double, right? So the conversion to double happens automatically. So I'm passing floats, but they will become double so that what I find in the parameter pack are only double. And it makes things easier. Rather than having multiple length for floating point type, I only have to deal with double. I will never find in a parameter pack a float, because when the caller built the parameter pack, if he saw a float, he actually added a double on this. So he sees a float that can be coded over 4 bytes, and he decides, no, I'm not going to do that. I'm going to use 8 bytes and convert my float into a double and use up 8 bytes of storage on my stack. At least it makes the implementation of the callee a little more reasonable. In the same way, if you see a bool, a character short, or any unscoped enumeration, they will be converted to an integer. So a bool only take 1 byte, a char is a byte, a short is 2 bytes. All these guys take 4 bytes. And it's very uniform. You only expect 4-byte integers on the type on your stack, right? So it's a very simple rule for doing the conversion. Now, is that an issue? Well, not really, because remember, VA arg is going to take as input the pointer that you start from and the type. So therefore, he knows full well the conventions. This reality that these conversions and promotions are happening are independent of you. VA arg, as long as he uses the correct type for doing the navigation, will be able to move through the parameter pack. You just need to be aware of this conversion rule so that you correctly use VA arg. Great. So now that we know this, let's take a look at the example. So this is a small piece of code. You have examples of VA list, VA start, VA arg, and VA end. Those are their spec, and this is the code. But let's directly go into Emacs and take a look at this in music on the implementation we were playing with just a second ago. So I'm going to take VaryFun again, and here, rather than this funny input, I'm going to go back to 5. And let's take a look at the function. So we had already seen the declaration, right? Nothing really shocking. My sum was taking NB, which is this, the number of values in the parameter pack. Then I have the ... the ellipse that stands for the parameter pack. When I'm inside my function, the first thing I say is, oh, I need an abstract data type. I'm calling it here args. You could pick whatever name you want. But I want this abstract value to be a variable argument list, because it's going to allow me to navigate the parameter pack. Now, once I have it, I need to initialize it so that it points to the beginning of the parameter pack, and I do it with a call to VA start, which takes, of course, my abstract value and the last argument that precedes the parameter pack. NB is the last thing that we saw before the ellipsis. So I need to pass the last argument that comes before the parameter pack in the prototype of the function. Once this is done, my VA list called args here, right? So this is the name of my VA list, it's args. And it basically refers to the beginning of my parameter pack. Once I have it, I'm going to actually do my computation. So I just want to sum up the values being passed. So I declare an integer total, and then I make a loop that says, let's loop our way back up, counting k going from 0 to nb, because I know I want to see 5 numbers. I will count 0, 1, 2, 3, 4, right? It's an open range loop as always. What we do here is we do TTL plus equal. So we increase the total local variable that started off at 0. And what is it picking up? Well, you notice that varg is taking two things. My parameter pack args, and at the beginning it's pointing here, and an int. So I'm saying with varg, I want to obtain a reference to the first thing on the parameter pack, and I'm telling you that this thing is an integer. So I know its type, and I know what kind of a reference I'm returning. I'm returning a reference to an integer. So this VA arg is a reference to this. It's a reference to the box that I'm highlighting now in blue, right? It's a reference to this box, and therefore I read the value that's there. It's an integer, it's 10, and I add 10 to my total. but it also has a second effect. It's moving args so that now args will be pointing just above that guy. It will be pointing to the next argument in the parameter pack. And it can do that because the stack is growing down. Because it's growing down, I add the address to the beginning of the value. So since I know the type of the value, I know that adding an integer on a 64-bit platform is 4 bytes. So I know that I need to work my way back 4 bytes, and now the blue pointer is pointing to the beginning of the memory cell where there is the next argument being passed. And there you have it. At the next iteration of the loop, I'm going to use my args, interpret that address as that of an integer, and I'm going to get a reference to the integer 20, read it, add it to the sum, and then compute the address to the next one. So args will now be pointing to this memory location. And the process repeats 5 times. By the time I'm out of the loop, the arg is pointing to the 50. I am done. I have read my entire parameter pack, so now I can use va-end, the third method of the abstract data type, to terminate the process, saying, I'm done with the parameter pack, I'm good, so I end this, and then I return the total I've computed. And that's all there is to it. So you see that this is a completely runtime process relying on va start, va arg, and va end to navigate the parameter pack. And the important thing is that the va arg here is using the type of the value so that you can navigate properly within the parameter pack. That allows me to get the correct behavior for the code. That's all there is to it. It's quite straightforward, and it allows us to do all sorts of beautiful things with variable argument list. Now, next time, in the next video, we're going to take that concept of variadic function and lift it to C++, where variadic objects turn into templates, and it comes with all sorts of goodies. For that, see you next time.